Good morning, students. Welcome to Real Analysis Live Lectures. In this lecture, we'll discuss about interior, exterior, interior of a set, closure of a set, limit point, boundary point, dense set, etc. Okay, so let's start. We start with a definition of what is meant by interior point. So take M is a metric space and A is a subset of M. Then we say that a point X in A is called interior if there is, say, suppose this is set A, then you take any point X from that set, then we say that this point is an interior point if we can find a ball around X, some ball, okay, such that which is completely contained in A. If this condition is satisfied for some epsilon, then we say that it is an interior point. And if we collect all interior points of A, that we can denote by A naught or interior of A. So what is this one? Some point will be here. If it is an interior point, that means a ball around X of some radius should be completely contained in A. Okay. Then you can observe that this interior of A is largest open set. First of all, you can observe that one we can observe is that this interior of A is clearly an open set. Why this is an open set? Because the way how we have defined here, if we take this one, then every point here X, if it is in A, then there is some ball around this. So therefore, that itself says that it is a open set. Because if you recall what is meant by say that U is open, if for every X in U there exists some epsilon greater than 0, such that Bx epsilon should be contained in U, right? So clearly this interior of A satisfies this condition, and hence it is an open set. Not only that, because it contains all such points, so this is the largest open set containing A, contained in A. What is meaning of saying that? So that means uh, if we say suppose what is meant by saying largest is that if U subset of A is open, then U is contained in interior of A. That's why this is in that sense it is called largest open set. One can easily prove that if U is an open subset, then we want to show that every element here is also here. But that follows clearly from by this definition, because this Bxu is contained in A U, so therefore X has to belongs to interior of A, right? Okay. You can easily see quickly some examples. Suppose if I take this A is the open interval 0 comma 1. Okay, so what should be our guess? At least that what are all interior points of this closed interval 0 comma 1. Clearly you can see that if I suppose take any point here, then I can find an open interval around this. If I take any point here, if I take any point here, then we can sense that they are all uh, interior points to that set, right? Okay, so in fact if you take any element here open interval 0 comma 1, then we can show that this X is actually is an element of interior, it is an interior point. Okay, why? It is very clear, because this 0 comma 1 open interval 0 comma 1, we know it is an open set. So therefore, and X belongs to here, so there exists a ball around X contained here, but here balls are nothing but intervals, so X minus epsilon to X plus epsilon is contained in 0 comma 1. Of course X is there. Okay, that shows that this X belongs to X minus epsilon comma X plus epsilon, which is contained here, and of course this is contained in 0 comma 1, which is A. Okay, so if you take this much part, that shows that X is an interior point. Okay, whereas if we take this end, this 0 or 1, however small open interval we try to take, you can see that some part is outside this set. Okay, so therefore this 0 and 1, 0 and 1 are not actually interior points. Remaining all points are interior points, so therefore interior of A is the open interval 0 comma 1. Okay, I hope this example you get some idea about how what is meant by an interior point. Okay, so for example, if you take any interval a comma b, okay, if you take a closed interval a comma b, then interior of this is nothing but open interval a comma b. Of course, if you take any other type of interval, okay, open and closed, for all these things interior is same. Okay, fine. uh, the other remark is that, very simple remark, if that set is already an open set, then interior of A is A itself, because interior of A is the largest open set contained in A, and if A is already open, then obviously interior of A is equal to A, right? Fine. Now take another example, interesting example. If you can understand this, then many examples you can do it, and you can understand how interior of a set look like. Okay, take this A is 1 upon n, so 1, 1 by 2, 1 by 3, and so on. Okay, right? So what is interior of this set? How it so if you plot it on an this real line, so you have 0 here and you have 1 here, 1 is there, 1 by 2, then 1 by 3, and so on. Okay, all belongs to here. uh, so whether any point of this element set is an interior point is the question or not. Suppose if I take this half for example, then question is, can we find a interval around that such that which is completely contained in A? Because this, however, you find out this is an interval which cannot be completely contained in this type of set, right? So we can at least sense that no point here is an interior point, so interior of A is empty. Why? So take any x in A, then any open interval around x is nothing but in real line x minus epsilon and x plus epsilon, which is an interval. We already proved that this is actually contains, every interval contains rational number as well as irrational number. Okay, so in particular it contains irrationals, whereas A does not contain irrationals, so this is not true, right? No interval can be contained in A. Therefore, no point of A is an interior point. Okay. Not only this, if you apply that logic, then interior of n, z, q, r minus q irrationals, for all these things, interior is an empty set. Why? You can argue for n, z, q the same way what we did here. If you take any x minus epsilon and x plus epsilon, okay, they contains irrationals, whereas n or z or q, they does not contain irrationals, right? So when you argue the same thing for irrationals, you take x minus epsilon and x plus epsilon, this contains rationals, whereas the r minus q does not contain rational, right? So anyway, interior of n, z, q, r minus q, this is an empty interior. Okay, you can go through it that, but that I have already explained it. This is about interior of a set. Now we come to exterior of a set. So that means, sorry, not exterior, closure of a set. We'll come to exterior or boundary later. So closure of a set. So start with A subset of M. Then what is meant by a closure of A, which we usually denote by A bar, or closure of A, CL of A, is nothing but the smallest closed set. So this is the smallest closed set containing A. Okay, so any set, a smallest closed set containing A, we call it as closure of A. We show it define in another way, which other books we say it is a bar is actually A union together with something called limit point, which we will define later. Okay, but all are same. We will see that, right? So first we start with what is meant by closure of a set is nothing but, if you take any A, then closure of A is the smallest closed set containing A. So whenever you want to, you talk about close smallest one, which are a closed set. Therefore, A bar you can write as intersection of all closed sets containing A. Then obviously this is the smallest closed set containing, right? Fine. Now we define what is meant by limit point so that we can relate this closure set in terms of limit point. So start with a set, then a point x belongs to M. So A is subset of M and x is a point of M. Then we say that this x is a limit point. X is a limit point of A if the every neighborhood of x. So every neighborhood of x, you can call it bx epsilon, contains a point of A other than x. Okay, so that means this A intersection from other than x, even after removing x from this ball, A should able to intersect this. Okay, and this should be true for every epsilon greater than 0. Then we say that it is a limit point. Okay, so simply saying limit point of a set is nothing but you take any ball around that point, then it should able to intersect that set A. Then we say it is a limit point of A, right? Okay, so now we'll try to uh, give a relation between this closure of a set and in limit points. For that, we'll start with this statement: x is in a closure of a set, x is in A bar if and only if ball around x, every ball around x intersects A. Okay, then we'll come to this relation with limit points. The proof is not at all difficult one. Suppose x is in A bar and we want to show that it is non-empty. Assume by contradictories there exists some epsilon greater than 0 such that this ball is not intersecting A. Okay, so that means Bx epsilon intersection A is suppose empty. Then this obviously A is contained in its complement, right? This complement of this ball. But sorry, this is C. But this is a closed set because Bx epsilon is open, so complement is closed set, right? And A bar, what we know about A bar? A bar is the smallest closed set containing A. That means because A bar is smallest, that means this is contained in this complement, right? But that is a contradiction because this x belongs to A bar. We have started with x belongs to A bar, so therefore we get that A bar is contained here. So x belongs to Bx epsilon complement, which is a contradiction because x is there in ball around x, so x cannot be in its complement, right? That contradiction arises because we have assumed that there is some ball. Okay, conversely also you can prove it. Suppose assume that Bx epsilon intersection A is non-empty for every epsilon greater than 0 if a ball intersects A itself, because then this Bx epsilon intersection A bar is also non-empty. Okay, for all epsilon greater than 0. That shows that A bar, since A bar is closed and this Bx epsilon intersection A bar is non-empty for every epsilon greater than 0, we get that x belongs to A bar, right? So what we have proved just now is that x is in A bar if and only if ball around x intersect this is non-empty for every epsilon greater than 0. Okay, now you can combine this one, so you can easily prove that A bar, which is closure of A, okay, is nothing but A union limit points of the set A. Okay, why? If you see if x is in A bar, then just now we proved that this intersects, right? So therefore this intersects, that means we can see that if x is not in A, then it is, if x is in A, then we are already done. If x is not in A, that means ball around x minus even x intersects A is non-empty. So that shows that x is a limit point of B, right? And you can easily say that if x is the limit point of A and if it is not part of this, then you will get this, so therefore it becomes here. So by this lemma, whatever we have proved here, by using this result, okay, we can easily write now a bar as, that means closure of a set A is A and together with limit points of that set. Okay, so closure of a set, what we can understand now is that set together with its limit points. Okay, for example, if you take 0 comma open 0 closed 1, then obviously its closure is closed 0 comma 1, because you can see that this 0 is a limit point, because however small ball you take around this part is there with this side, okay, which always intersects this A, right? Therefore 0 is a limit point of this set. If you take open interval 0 comma 1, then for this is closed 0 comma 1. If you take this 1 by n, this set which we have already discussed, for this you can check that 0 is a limit point. Okay, 0 is a limit point, because if you take 0, then around this, whatever however small you take, there will be many points of this form 1 by n which are here. Okay, so therefore this set, if you call it this set as A, then uh, minus epsilon to epsilon, this intersection A is always non-empty. You can always show that. That means you can always find whatever epsilon greater than 0, can you find 1 by n, okay, which belongs to here is the question, and that is always happens. Okay, what is that? Archimedean property, right? Now, and we can also give the characterization of uh, element in a bar, that means closure of a set, in terms of sequence. What is that? It says that x is a closure of that set if and only if there exists a sequence xn in A such that xn converges to x. Okay, and this proof is not at all difficult one, which we have already discussed similar type of thing. What we want to see is that the overview we can quickly see it. If x is in a bar, x is in a bar, just now we proved a lemma, it intersects every open ball around x, right? In particular, now take epsilon is equal to 1 by n form, then you will have every time one element, you can call it xn, which belongs to bx epsilon intersection A and so on. Then you can see that easily that xn converges to x, right? And these xn's are all coming from A, so therefore there exists a sequence converging to x. Conversely, if xn is a sequence in A such that xn converges to x, okay, then we want to show that this x belongs to a bar. Okay, how you can show that? You can easily, by using this lemma, whatever we have proved, it is enough if we show that every ball around x intersects A, and that is what we can prove it here. You can see that every ball around x intersects A, and hence x belongs to a bar. So that one result about closure of a set is very very important. X belongs to a bar if and only if every ball around x intersects E for every epsilon greater than 0, right? Okay. Now this is something about a relative metric, which we just define it and we'll use it whenever it comes later. What is relative metric? So you take m comma d is a metric space. So what is meant by saying that? D maps from m cross m to R or close 0 to infinity, satisfying some conditions. Now you take A, which is a subset of M. A is a subset of M. Then D you can restrict to A. That means A cross A to R. Okay. If you consider this map, then obviously we can get a metric on A. Okay. That we will call it as a relative metric. Okay. So this A together with D restricted to A, this is called a relative metric. So what we are doing is we are restricting our domain to A cross A. Okay, and whenever without any confusion, instead of writing D restricted to A, we can simply write A comma D. Okay, uh, then how open balls look like in this relative metric is that, suppose you consider this is a point x. Okay, this is a ball around x of radius epsilon, and see you have some m here, right? Now assume that this is this much is your E. Okay, then uh, what should be the ball around X? Okay. So sorry, you should extend your this much. See, so that X should be in A. Okay. So ball around X of radius epsilon in A. How it look like? That means we are trying to know how a ball is there with respect to this relative metric. Okay. So if this is my set A, okay, and this is my X, then what is ball around X of epsilon radius with respect to E is nothing but obviously what we guess is that whatever this ball which is part of A, because it should be contained in A, so what is this much you can consider as, so whatever this blue color we have shaded, okay, this much is ball in A, ball around X in A. So this is your Bx epsilon but with respect to A, right? So how we can write? We can write it as distance between any, you take any point y in A such that distance of x comma y is less than epsilon. So as we said, relative metric, we are restricting points to A. So not any y belongs to M. Here we have to take y is in A. That is same as saying that this A intersection in this way you can write. So ball around x in A is same as ball around x in M, okay, intersect with A, right? Fine. Now, using this definition, one can prove that a set, you take a subset of M, then you can talk about a relative metric here and a metric here. So therefore, G subset of A is open in A if and only if we can write this G as some A intersection U where U is open in M. Similarly, F subset of A is closed in A. Okay, if and only if F can be written as A intersection C where C is closed in M. So any open set in A is actually can be written as A intersected with some open set. Okay. This proof is not at all difficult. Suppose G, you start with G. I'll explain this first one. You can similarly you can do it second one. So start with G is an open set, non-empty open set. We want to write G as A intersection U, right? Because this is non-empty. Take X is in G and G is open in A. That means there exists some radius such that Bx epsilon A is contained in G, and we have proved a result saying that if G can be written as union of such balls, okay, union of such balls. But now this is same as A intersection Bx epsilon, and using distributive properties you can write as this A intersection union of this such balls, right? So if you consider this union as union of balls is open set is open, so therefore A intersection U where U is this, you can write G as in this way. Okay. Then conversely, suppose G is of the form A intersection U where U is open in M, we want to show that G is open in A, right? So to show something G is open in A, you start with X is in G. We want to find some ball which is completely contained here. But X, because G is A intersection U, so X is in A as well as X is in U. Now U is open, so there exists a ball which is completely contained in U, right? This implies if you intersect with A, then this is also there, right? But this is same as Bx epsilon A, okay? This is, sorry, this is contained, okay? Bx epsilon A, right? Now, but our U intersection A is nothing but our F, this G, sorry, right? That proves that what we have proved, that if we start with X is in G, then we found a ball around X in A, which is completely contained in G. Therefore, this shows that G is open. Same way you can prove it closed, but that I'll skip here. You can check it. It's not a problem, right? Fine. Uh, you, so far what we have seen is we have seen a closed set, Okay, of course, open set. Then we have seen what is meant by interior of a set, then closure of a set, limit point, right? Now there are some other points which we can relate. Is one of them is called a boundary point. Okay, so what is meant by a boundary point? That name itself suggests that it should be a boundary. That means you say that an x belongs to M is a boundary point of A if every ball around X should intersect A, as well as every ball around X should also intersect A complement. Then we say that it is a boundary. That means if you just go this side, it should be in A. If you go just other side, it should be in A complement, and so on. Okay, then we will call it as a boundary point, right? For example, if you take in real line, if this is your R, and A, if you take as suppose something called open interval 0 comma 1, then you can see that this 0 comma 1, if you take it, then 0 is a boundary point as well as 1 is also boundary point, because however small ball you take, it has some part with outside A and some part is inside A, and so on, right? So for this A 0 comma 1, what is boundary of A is this set 0 comma 1. 2 points are there which are boundary points for this, right? If you take any point outside this, clearly you can find a small neighborhood which is completely outside, right? So therefore this point cannot be. Similarly, if you find anything here, they also cannot be boundary points. So only 2 points are there, which is 0 and 1. They are boundary points. Okay, and so you can try to find n number of examples. Say suppose take n, z, q, this set 1 by n. Okay, exercise is that find boundary points. So boundary of points of this set n, z, q. What are the boundary points? Try to find it. Okay, now we can relate this whatever we have seen. The boundary of any set is nothing but from closure. So you can write closure of A. From this set you remove interior of A. Okay, or you can also write closure of A is boundary. This is boundary, not so boundary of A union with interior of A. And the entire set metric space M you can write as interior of A, then boundary of A, then interior of A complement. Okay, so these are the relations you can easily verify with examples or how you can prove things and so on. Okay, at least one we have seen boundary here, so I'm not going to explain things, but you try to see why boundary of n is n itself, q is r, boundary of r minus q is r. So these are very good exercise. Just think of if you take any rational number, okay, any irrational number also, then it should be boundary of this one is entire r. So you try to see why it is true. Okay, fine. Now the other one is a dense set. The other interesting set is a dense set. So start with A subset of M, then we say that A is called dense if the closure of A is the whole metric space. Okay, that means A together with, if you consider its limit points, that should be closed, that is equal to M. Okay, then we say that A is dense. So in the other sense, what is meant by a limit point? So limit point means however small ball you take, it should intersect that M, right? That then we say it is a limit point. So A together with limit points equal to M. That's why we call it as this dense. In the sense, the elements of A, are there everywhere in M. Okay, so wherever you go, so this, suppose if I say this is M, if I take any point here, then we are able to see that you can able to find a ball around this, okay, which intersects A. Okay, that means there is a ball around X where at least some points are belongs to A, right? In that sense, we say it is a dense set. So elements of A are spreaded at every corner of this M, right? Okay. So this is the mathematically the definition that Bx epsilon intersection A should be empty for every epsilon greater than 0. Okay. You can check that Q is dense in R. Why Q is dense in R? Because Q union together with limit points of Q, this should be equal to R, right? You can check that limit points of Q, every R minus Q, every irrational number is also a limit point of this Q. Okay, because why? If you take any X which is R minus Q, why it is a limit point of Q? Whatever ball you take, whatever interval you take, obviously this intersection Q is non-empty, because every interval contains infinitely many rationals as well as irrationals, right? So therefore, you can see that Q is dense. Similarly, R minus Q is also dense, whatever we have explained in this sense, right? Check whether exercise is whether Z or N, whether they are dense sets. You can just think whether they satisfy this property or not, whether Z bar is equal to R, whether Z bar, so this is same as asking whether Z bar is equal to R or whether N bar is equal to R, right? Okay, by this time at least you should know the answer. Now the other one, the last one which for this lecture is nowhere dense. Okay, so nowhere dense is not same as not dense set. So nowhere dense in the sense the elements are not closely put, okay, not compact in that sense. So you take A subset of M, we say that this is nowhere dense if the closure of its set, okay, so that means if you write A bar, then if you consider its interior, this should be empty, okay. That means a set is said to be nowhere dense if its closure has empty interior. You take the closure and consider that set, for that set interior should be empty set. For example, if you take N, then you can see that this N is nowhere dense, okay. Why? What is N bar? That means what is closure of N? N together with its limit points, you can check that no this thing, you N bar is N itself, then interior of N is empty, okay, right? So therefore this, so you can check what can you say about Z, whether Z, this 1 by N, okay, are they, are these sets nowhere dense? So if they are nowhere dense, then why? If not, then what is the reason? Okay. So in next class, we'll discuss about continuity in a metric space. Okay.